Welcome to the Deep Dive. Today we're really getting into the nuts and bolts, literally, of aircraft maintenance, metal structural repair. If you're working towards that airframe ticket, understanding Chapter 4 inside and out is, well, it's non-negotiable. We're aiming to make that a bit easier today.
Absolutely. This is where theory really meets practice, right? On the hangar floor. Modern planes, they fly because of precise sheet metal work. We're talking mainly high-strength aluminum alloys fastened together meticulously. Our goal here is clarity, giving you the core knowledge to restore damage properly. It boils down to duplicating three things perfectly: original strength, material type, and the exact dimensions.
Right. So we'll navigate through the essentials of structural integrity, understanding the forces at play. We'll start with those forces, then dive into the precision tools needed for layout, measuring, all that prep work. Then we'll cover actually shaping the metal cutting, grinding, forming. After that, it's all about fastening, especially riveting the rules, the techniques. And we'll wrap up looking at some trickier materials like titanium, magnesium, and the all-important inspection and compliance side.
Good plan. And maybe just one quick point before we jump in, something fundamental about materials. Sheet metal thickness. It's defined by gauge. You'll usually see gauges from maybe 8, which is quite thick, down to 30, which is very thin.
Right.
The key thing, and it trips people up, is it's counterintuitive. The higher the gauge number, the thinner the metal.
Right. So 30 gauge is much thinner than 10 gauge.
Exactly. Get that wrong. Call for 18 gauge, but install 24. You've instantly compromised that repair. Big mistake.
Okay, good point to start with. Let's talk structure then. Thinking about the forces an airframe endures, we see damage from static loads sometimes, right? Like something dropped on a wing. But what happens in the air with those dynamic loads?
Yeah, the whole picture changes. On the ground, you've got the static weight pushing down fuselage, fuel, engines. But once airborne, lift dominates, pushing upward. And that lift force, it doesn't just push evenly, it follows a very specific path.
Okay, so where does it go first?
It hits the skin first, and the stringers, those lengthwise reinforcing members, they take that initial load.
And from the skin and stringers,
Then what?
then it gets transferred inwards through the ribs.
Yeah.
The ribs are what give the wing its airfoil shape.
Right.
From the ribs, the load moves into the main structural members, the heavy-duty spars. They run span-wise, and the spars carry that load right into the fuselage structure. Understanding that path, skin, stringers, ribs, spars, fuselage, is absolutely crucial. Your repair can't block or weaken that flow. You mentioned stringers. Maybe we should quickly clarify the difference between stringers and longerons. Sometimes students mix those up.
Good idea. So stringers are generally lighter, more numerous members running fore and aft. Their main job is to stiffen the skin, stop it from buckling, and they carry some of the bending loads.
Good.
Longerons are the big guys. They're the main heavy fore and aft members, often at corners or key points in the fuselage frame. They take the major longitudinal stresses.
So repairing a longeron is a much bigger deal.
Oh, absolutely. Much
Yeah.
more complex, much higher structural significance.
And it's interesting, you look at a wing, it seems so solid, so rigid.
Uh,
But the source material points out it actually acts more like a leaf spring. It bends.
It does. It's designed to flex upwards, sometimes quite a bit, several feet on larger aircraft. And you might even see a little flutter. That's normal.
Really? Flutter is normal.
Slight flutter, yes. That movement is part of the design. It helps dissipate stress and energy. So when you're doing a repair, you have to make sure the materials and the way you install them allow for that intended flex.
What happens if you don't? If you make it too stiff?
Big problems. You create a hard spot. That spot won't flex with the rest of the structure, so it attracts stress. It becomes a stress concentration point. And that's just asking for fatigue cracks to start, often just outside your nice stiff repair.
Okay, makes sense. So let's nail down the types of stress these components are constantly fighting. The sources list 6 fundamental types.
Right, and we usually group them into 2 categories. First, the 4 basic ones: tension, compression, shear, and bearing.
Tension, compression, shear, bearing. Got it.
Then you have the 2 combination stresses: bending, which is a mix of tension and compression, and torsion, which is twisting. The really important thing for a technician to grasp is that these stresses almost never act alone in the real world.
Right, they combine.
Exactly. Think about an engine mount. It's probably seeing tension from the engine pulling forward, shear on the bolts holding it, maybe even some torsion from engine torque. It's complex.
Let's zoom in on tension for a moment, because understanding tension is key to figuring out riveted joint strength, right?
Definitely. Tension is basically that pulling force. Trying to stretch the material, pull it apart, like the engine pulling the plane forward against the drag, trying to hold it back. That puts parts of the structure in tension.
And we measure how strong a material is in tension using psi, pounds per square inch.
Correct. Tensile strength is measured in psi. You calculate it by taking the load needed to break the material and dividing it by the original cross-sectional area of the piece.
Okay, now here's something the sources really emphasize, and it sounds critical for repair calculations.
Yeah.
The difference between gross area and net area.
This is absolutely vital. Get this wrong, and the repair calculations are meaningless. See, the original design strength is based on the gross area, the total area of the metal's cross-section before you do anything to it.
Oh yeah, the whole piece.
Right. But the second you drill a hole for a rivet or bolt, you've removed material, load-carrying material. The net area is what's left. It's the gross area minus the area of those holes you drilled.
And why is that distinction so critical when calculating tensile strength? Doesn't the rivet help carry the tension across the hole?
Not really, no, not in tension. A rivet or bolt is primarily there to transfer shear loads to stop the plates sliding past each other. It doesn't effectively carry that pulling tensional load across the gap created by the hole.
Ah, okay.
So when tension pulls on that riveted joint, it's only the remaining metal, the net area between the holes, that's actually resisting the pull. If you have, say, a 0.040-inch thick skin and drill a 18-inch hole in it, you've permanently weakened that specific spot in tension. Your repair design, like using doublers, has to account for that, making sure the load gets safely transferred around the hole through the remaining net area.
That detail about net area flows perfectly into the next phase, preparation. Before you can even think about cutting metal, you need precise layout and measuring.
Precision is everything here, and it starts with the basics, like a simple steel rule or scale. A good shop technique, because the ends of scales get worn or damaged, is this. Hold the scale on edge so the marking lines are right against the metal.
On edge, okay.
And don't measure from the very end. Start at the 1-inch mark. Then just subtract that inch from your final reading. Avoids errors from a potentially damaged end.
Simple, but effective. Now, for more complex layouts, angles, and finding centers, the combination square comes in. It's more than just a 90-degree tool.
Oh, much more. It's really 3 heads in one tool. You've got the standard stock head that gives you your 90s and 45s quickly. Then there's the protractor head, lets you set or measure any angle you need.
Right.
But the really clever one is the center head. If you need to find the exact center of a round piece, like a shaft you're about to drill,
Yeah. How does that work?
you put the round stock into the V-notch of the head, scribe a line along the ruler edge, then rotate the stock about 90 degrees, keep it in the V, and scribe another line where those 2 lines cross. That's your dead center. Perfect alignment before you even reach for a punch.
Nice. What about laying out patterns, especially rivet lines, quickly?
Dividers are essential for transferring measurements accurately or scribing circles, but for laying out rivet patterns fast, especially along a long seam, the rivet spacer is your friend.
Rivet spacer. Okay.
Yeah. These tools usually have preset marks for common spacings, 1/2 inch, 3/4, 1 inch, maybe 2 inches. You just align it on your center line and mark off your rivet locations. Saves a ton of time compared to measuring each one individually.
Okay, layout tools covered. Now, a really critical safety and maintenance point, marking the metal itself. We need to talk about the pencil problem.
Right.
Why is a standard pencil bad news on aluminum?
This is fundamental. You never use a regular graphite pencil, like a known tube pencil, directly on aluminum alloy.
Why not?
Graphite is carbon. When carbon touches aluminum, especially if there's any moisture around, it sets up galvanic corrosion. The graphite acts like a cathode, the aluminum an anode, and the aluminum starts corroding.
Ah, okay. So what should we use?
The preferred method is a fine-tipped permanent marker, like a Sharpie, or mark on masking tape that you've applied to the surface first, then peel the tape off later. Both avoid the corrosion risk completely.
Good to know. And what about scribes, those sharp tools for scoring lines? There's a strict rule about using them, isn't there?
Absolutely non-negotiable. A scribe makes a scratch. Any scratch on aircraft skin, especially stressed skin, is a potential starting point for a fatigue, crack, or corrosion. It's a stress riser.
So the rule is?
You only use a scribe where the mark you make will be completely removed by the next step. Either you're cutting along the scribe line so the scratch material is gone, or you're scribing the center of a whole location and the drilling operation removes the scribe mark. Never, ever leave a scribe mark on a finished part surface.
Got it. Lines marked, locations identified. Now we need to prepare those locations for drilling using punches. Seems like there's a sequence here.
There is. You start with the prick punch. It has a very sharp, slender point. You use it for the initial layout, making a tiny, precise mark right at the center point of your intended hole. It's also really useful for transferring dimensions from a paper pattern onto the metal.
Okay, prick punch first for precision.
Then, just before you drill, use a center punch. Its point is a bit blunter, maybe 90 degrees compared to the prick punch's 60. You tap it into the prick punch mark.
And why enlarge the mark with the center punch?
That creates a slightly larger indentation, a little conical seat. That seat guides the very tip of the drill bit and stops it from walking or skidding across the surface when you start drilling. Keeps the hole exactly where you intended it.
Makes sense. Any precautions at the center punch?
Yes, don't hit it too hard. You just want a clear indentation for the drill tip. If you whack it so hard you dimple the surrounding metal or push the mark through to the other side, you've distorted the material, which is bad. Gentle but firm tap is all you need.
Right. And the third type mentioned is the transfer punch. What's its specific job?
Transfer punches are usually used when you're mating a new part to an existing structure that already has holes. They come in sets with precise diameters matching standard hole sizes. You put the transfer punch into the existing hole in the underlying structure, then tap it. It marks the exact center of that existing hole onto your new piece of material.
Ah, so it guarantees the new holes line up perfectly with the old ones.
Exactly. Essential for accurate alignment in overlap repairs.
Okay, layout and marking are done. Now we actually have to shape this metal. Let's talk cutting tools first. What are the go-to tools for removing larger amounts of material or making complex cuts?
Well, for bigger jobs, especially things like cutting out damaged stringers or making curved cuts in thicker sheet, maybe up to 316-inch aluminum, the cat saw is very popular.
CAD saw. What's special about it?
It's portable, electric, and the key feature is its rotating cutting head. You can turn the head to cut at almost any angle without moving the saw body much. And importantly, you don't need to drill a starting hole. It can plunge cut. There are also pneumatic circular saws and reciprocating saws used for similar tasks.
Okay, CAD saw for heavier cuts. What if you need to make really intricate shapes, maybe cutting out small internal sections?
That's where a nibbler shines. Nibblers work with a kind of rapid punching action, like a tiny punch and die.
Crunching.
Yeah, they punch out tiny slugs of metal, maybe only 1/116th of an inch wide, very quickly. Because it removes such small pieces, you can follow very complex lines, curves, and internal cutouts. You're basically nibbling your way through the metal. Leaves a clean edge.
Interesting. How do those compare to shears, which seem more for straight line cutting?
Right, shears are different. You've got the big stationary squaring shear in the shop. That's for making long, straight, accurate cuts and ensuring your material edges are perfectly square. Often has guides for repeatability.
Okay, the big chopper.
Exactly. Then you have the incredibly versatile throatless shear, like the Beverly brand shears people might know.
Throatless.
Yeah, the name says it all. It doesn't have a throat or frame limiting the depth of cut. This means you can feed a sheet of metal of basically any size or shape into it.
Ah, so you can cut large pieces or follow irregular curves easily.
Precisely. Things you could never do on a standard squaring shear. And for smaller work, you have hand tools like straight snips for straight cuts or large curves, and aviation snips, which have compound leverage and are better for cutting circles and tighter arcs.
Got the cutting covered. Now, finishing the edges, filing takes time. Are there faster ways like sanders? And what's the deal with wet grinders?
Yeah, disc sanders and belt sanders are definitely faster than hand filing for trimming parts down to the exact dimension after rough cutting. The wet grinder is used specifically when you need to remove material accurately but without overheating the edge. Heat can ruin the temper, the heat treatment of the aluminum alloy.
So the water cools it.
It does three things, really. One, it cools the edge constantly, preventing that heat damage. Two, it acts as a lubricant, making the grinding smoother and faster. And three, it washes away the metal particles and grinding debris, keeping the wheel clean and giving you a better finish.
Okay, but sometimes you still need to file. What should we know about files? Different types, coarseness.
Files are classified in a couple of ways. First, by the pattern of the teeth. Single-cut files have teeth going in one direction, generally for a smoother finish. Double-cut files have two sets of teeth crossing each other, making them more aggressive for faster material removal.
So you go in double cut. Okay.
Then they're graded by coarseness. It ranges from rough and coarse through bastard cut, second cut, smooth, all the way down to dead smooth for very fine finishing.
And specific techniques. The sources mention cross-filing and draw filing.
Right. Cross-filing is the normal way you'd use a file, pushing it more or less perpendicular to the edge you're working on. Good for bringing edges down to a line. Draw filing is different. You hold the file handles at roughly 90 degrees to the direction you're moving it, and you draw it sideways along the length of the surface. It gives a very smooth, flat finish. Great for squaring up large surfaces after bending.
All right, let's move into forming, creating bends and shapes. We need specialized machines for this, starting with brakes for making straight bends.
The simplest is probably the bar folding machine. It's for light gauge metal, maybe 22 gauge max. Good for making small hems or simple flanges like folding an edge over.
Okay, for light stuff, what about the standard shop brake?
That would be the box and pan brake, often called a finger brake. This is the workhorse for most structural sheet metal bends.
Why finger brake?
Because the upper clamping bar is made of individual removable segments called fingers. You can take out specific fingers, which allows you to bend up the sides of a box or pan shape. The metal can bend up past the gaps where you removed the fingers.
Ah, clever. Allows you to make four-sided shapes.
Exactly. You often need custom nose radius pieces or shims on the fingers to get the exact bend radius specified in the repair manual.
And for really heavy-duty stuff, thick material, complex channels like stringers.
Then you need a press brake. These are much more powerful, usually hydraulic. They use specialized upper and lower dies to form thicker material, maybe up to 0.090-inch annealed aluminum, or even something strong like 0.063-inch 7075-T6. Essential for making things like heavy U-channels or the hat section stringers you find in fuselages.
Okay, that handles straight bends. What about curves, like forming a cylindrical piece or a gentle arc in a skin panel?
For that, you'd typically use a slip roll former. It has 3 rollers. You feed the sheet between the top 2 and the single rear roller. The position of that rear roller determines the radius of the curve.
Is it easy to set?
Not really. It's mostly trial and error. You adjust the rear roll, run a test piece through, measure the curve, adjust again. You keep tweaking it until you get the exact curvature needed for the part. There's no direct dial for make this diameter.
Patience required. What about creating those smooth, gentle crowns you see on things like wing leading edges or fuselage skins?
That's often done with an English wheel. This machine uses 2 wheels, typically a large flat lower wheel, and a smaller crowned upper wheel. You roll the sheet metal back and forth between them under pressure. It gently stretches the metal, allowing you to shape those large, low-crowned panels. It's also great for planishing, which is smoothing out parts that might have been rough formed with hammers, getting rid of marks, and creating a really smooth finish.
Okay, some specialized tools. Now, let's touch on a couple of specific forming techniques mentioned. The piccolo former and the joggle.
The piccolo former is more of a detail tool. It's used for cold forming on profiles or extrusions, good for working out small wrinkles or doing very localized shrinking or stretching. When talking about general shrinkers and stretchers, whether they're the foot-operated floor units or hand tools, the key is finesse. Don't try to get the shape you need in one big go. You'll likely overstress the metal, cause excessive work hardening, maybe even crack it. The better approach is a series of small incremental shrinks or stretches, working the area gradually into the shape you need. Gives a much better, more stable part.
Makes sense. And the joggle, that little offset bend, what's its purpose?
The joggle is all about fit and finish. It's an offset formed into a part, usually near the edge, so that it can overlap smoothly with another sheet or fit snugly against a structural member like a frame or stringer.
So it keeps the outer surface flush.
Exactly. Maintains aerodynamics, prevents things from snagging. The geometry is important. For a simple joggle in a flat sheet, the rule of thumb for the flat distance between the 2 bends making the offset is about 4 times the thickness of the material being displaced or overlapped.
4 times? What about on stiffer parts like extrusions?
Because extrusions are stiffer, you need a longer transition. The allowance there can be much larger, maybe up to 12 times the material thickness, to avoid putting too much stress into the part.
And how do you make joggles, especially on curved parts?
For complex shapes or flanges, you often use joggle blocks. These can be made of hardwood, steel, or aluminum. You clamp the part to the block, which has the negative shape of the joggle, and carefully tap the offset into place with a mallet or hammer.
Okay, part formed, joggled perfectly. Now we have to attach it. Let's dive into riveting, starting with choosing the right rivet. Alloy matching seems key.
It's the first rule. Whenever feasible, use rivets made of the same alloy as the parts you're joining. So if you're riveting 2024 T3 skin, ideally use 2024 rivets. If it's 1100 or 3003 material, use 1100 rivets.
Why is that so important?
Two main reasons: maintaining the design's structural strength and, crucially, preventing galvanic corrosion. Mixing dissimilar metals creates a battery, especially with moisture present, and the more active metal will corrode away. Sticking to the same alloy avoids that.
Okay, same alloy. Now, how do we figure out the right diameter for the rivet? There's a rule mentioned, the rule of 3.
Yes, the rule of 3 is your starting point for rivet diameter. It's simple. Take the thickness of the thickest sheet you're joining. Actually, wait, check that. It's usually based on the thinnest sheet, typically the skin for repairs. Multiply that thickness by 3.
Thickness times 3.
Right. Then you choose the next larger standard rivet size. Rivets come in 132-inch diameter increments.
Can you give an example?
Sure. Let's say you're riveting 0.040-inch thick skin. Multiply 0.040 by 3, you get 0.120 inches. The standard rivet diameters go 332, 0.0949, 18, 0.125, 532, 0.156. So the next size larger than 0.120 is 18-inch, or 0.125. You'd use a 18-inch diameter rivet.
Got it. Thickness by 3, then next size up. What about the length?
Rivet length is critical too. It needs to be long enough to pass through all the layers of material, that's the grip length, plus have enough extra material sticking out to form a properly shaped shop head on the backside.
And how much extra material is needed for that shop head?
The standard formula is the extra length needed is 1.5 times the rivet diameter, 1.5 D.
Around 0.5 times D.
Yes. So for that 18-inch, 0.125 diameter rivet, you need 1.5 times 125, which is 0.1875 inches, or 316 of an inch, sticking out past the grip length to form the head correctly.
Okay, diameter and length sorted. Now, layout. How far apart should rivets be and how close to the edge? Let's talk edge distance first.
Edge distance, the distance from the center of the rivet hole to the edge of the sheet, is super critical. Too close, and the metal might crack or tear out when the rivet is driven or under load.
So what's the minimum?
Absolute minimum edge distance is 2 times the rivet diameter, 2D. However, the preferred edge distance, giving a bit more margin, is 2D plus 1/116th of an inch.
2D minimum, 2D plus 116 preferred. What if you go too far from the edge?
If the edge distance is too large, the sheet metal between the rivet and the edge might lift or curl up, especially under compression loads. It won't be properly supported.
Okay, edge distance nailed down. What about the spacing between rivets in a row? That's called pitch, right?
Correct. Rivet pitch. The minimum pitch depends slightly on the pattern, but generally the absolute minimum is 3 times the rivet diameter, 3D. This prevents the holes from being too close and weakening the sheet excessively between them.
So never closer than 3D.
Right. In practice, for most repairs, the pitch will be somewhere between 4D and 6D. You might use closer spacing, down towards 3D, in areas with high compression loads to provide more support to the skin and prevent buckling between rivets. But 4D to 6D is a common range.
All right, layout done. Now drilling the holes. We talked about center punching, but what about the drilling itself? Any common pitfalls?
2 big ones. First, especially for larger holes, say 316-inch and bigger, you should always drill a smaller pilot hole first.
Why a pilot hole?
It helps guide the final, larger drill bit more accurately and reduces the force needed. The trick is choosing the right pilot bit size. It should be about the same width as the chisel edge at the very center of the final drill bit. Too large a pilot bit can actually dull the main cutting edges of the final bit.
Okay, pilot holes for larger sizes. What's the second pitfall?
This one's huge. You absolutely must hold the drill perpendicular at a 90-degree angle to the surface you're drilling.
Why is being perfectly perpendicular so important?
If you tilt the drill even slightly, one cutting edge of the bit bites more than the other. The result is an elongated hole, kind of egg-shaped instead of perfectly round. That elongated hole won't support the rivet properly, drastically reducing the joint's shear strength. It's a major defect.
90 degrees.
Right.
Critical. After drilling, there are always burrs left around the edge. Removing them seems important.
Non-negotiable. Burrs must be removed. You can use a deburring tool, a scraper, or even just carefully rotate a larger drill bit by hand in the hole.
Why are burrs such a problem?
Several reasons. They prevent the parts from fitting tightly together, no fang surface contact. They can scratch the protective coating off the rivet shank as it's inserted, inviting corrosion. And maybe worst of all, burrs trapped between sheets create tiny gaps. These gaps allow movement, fretting, and trap moisture, leading to corrosion and potential fatigue failure right there in the joint.
Okay, deburring is essential. Now, for flush riveting, common on external surfaces for aerodynamics, we either countersink or dimple. Let's start with countersinking.
Countersinking involves cutting a cone-shaped depression into the top sheet of metal so the flush rivet head fits perfectly level with the surface. The standard tool for this is a microstop countersink. It has an adjustable cage or foot that rests on the surface and precisely controls the depth of the cut, often adjustable in thousandths of an inch. This ensures the rivet head is perfectly flush, not too high or too low. The standard angle for aircraft rivets is 100 degrees.
What about that annoying chattering sound and the rough finish it leaves sometimes?
Yeah, chattering is a common issue. It's basically vibration of the cutter. The main causes are a dull cutter, running the drill too fast, or not applying steady, firm pressure.
So the solutions are?
Sharp tool, slow speed, steady pressure. Sometimes using a pilot hole that's correctly sized helps. Using a cutter with more flutes can also sometimes reduce chatter.
Okay, but what if the top sheet is too thin? If countersinking would remove too much material and leave a weak knife edge?
Right. If the material is too thin to safely countersink, generally less than the head height of the rivet, you have to dimple. Dimpling doesn't remove material, it forms it. You use a male die, punch, and a female die, usually in a set. These press an indentation into the sheet that matches the shape of the rivet head.
How is dimpling done?
It can be done with hand squeezers for thin material or pneumatic squeezers or even stationary presses. The key is that both the top sheet and sometimes the sheet underneath are formed together to accept the flush rivet head. The sources also mention coin dimpling as an alternative if proper dies aren't available. You basically use a countersunk rivet itself as the male die and hit it with a pneumatic hammer. It's considered less precise and more of a field or emergency method.
Got it. Countersink for thicken up material, dimple for thin. Now let's drive that solid rivet, usually with a pneumatic rivet gun, right? What about the bucking bar?
Yes, the pneumatic rivet gun provides the impact force, usually running on 9100 psi shop air. You fit interchangeable rivet sets or headers into the gun that match the shape of the manufactured head, like universal head or flush head. But the bucking bar, held on the other side against the rivet shank, is just as important. It provides the reaction mass. The person using it, the bucker, doesn't just hold it there, they guide it and let its weight and rebound action form the shop head.
What's the critical technique for the bucker?
Alignment. The bucking bar must be held flat and square, perfectly at a right angle to the rivet shank during the entire driving process.
What happens if it's tilted?
If the bucker tilts the bar, the shop head will be formed unevenly, a clinched or sloping head. The shank might bend, or the bar could slip off and damage the surrounding skin. Proper alignment is key to a good shop head.
After driving, we inspect. What if we find a bad rivet? Maybe the head is cracked, the shank is swollen, or, like we mentioned, the hole got elongated during drilling. What's the fix?
If the rivet itself is defective, or if the hole is damaged, elongated, scratched, the standard repair procedure is to carefully drill out the bad rivet and replace it with the next larger size rivet.
Next larger size.
Yes. That usually means going up 132nd of an inch in diameter. So if it was a 18-inch rivet, you'd drill the hole out cleanly to 532-inch and install a 532-inch rivet. This removes the damaged hole material and ensures the new, larger rivet provides the necessary shear and bearing strength for the joint.
Okay, that covers solid rivets. What about situations where you can't get to the backside? That's where blind rivets come in.
Exactly. Blind rivets were a game changer, developed by Cherry back in the 1940s for those inaccessible locations. But, and this is a big but, they have significant limitations. Technicians must know this. Unless the aircraft's Structural Repair Manual, SRM, specifically authorizes their use in a particular location, blind rivets generally cannot be used in fluid-tight areas, in engine air intakes, on flight control surfaces, or in any location subject to high tensile loads or significant vibration. They are primarily for shear applications in secondary structures.
And there was a big improvement in blind rivet design, moving from friction lock to mechanical lock.
Huge improvement. The older friction-locked blind rivets relied solely on friction to hold the center stem, the mandrel, in place after installation. Problem was, vibration could cause that stem to loosen and even fall out, drastically reducing the rivet's strength.
Yeah, good.
Definitely not. So modern standards generally require mechanical lock types, like the Cherry Max is a common example. These have a locking collar that physically swages or locks a stem into the rivet sleeve during installation. You can often visually inspect that the lock is formed correctly, much more reliable and resistant to vibration.
Okay. Beyond blind rivets, there are also high-strength pin fastening systems like high-loki or high-teague. They look almost like bolts, but without threads.
That's a good way to think of them. They're two-piece fasteners. A pin, which has shallow locking grooves instead of threads, and a collar, which is swaged onto those grooves during installation using special tooling. They provide very high shear strength, often used in critical structural
Or
joints.
are they installed differently?
A key difference, especially in aluminum structures, is that they often require an interference fit. The hole is drilled slightly smaller than the pin diameter.
Interference fit, meaning the pin is forced in.
Yes, but it's a very controlled amount of interference, usually only up to about 0.002 inches for aluminum. Too much interference would overstress the aluminum. The high teague version is interesting. It has a small bead or radius near the pin head. As that pin is pulled into the interference fit hole, that bead cold works the metal around the entrance of the hole.
Cold works, what does that do?
It creates a zone of residual compressive stress right around the hole edge. This makes the hole significantly more resistant to fatigue cracking starting from that point. It enhances the fatigue life of the joint.
Fascinating stuff. We've mostly talked aluminum, but aircraft use other metals that present unique challenges. Let's start with stainless steel, or CRES.
Corrosion-resistant steel is tough stuff. Strong, but hard to work with. For shearing or punching, it takes roughly twice the force compared to mild carbon steel.
And drilling it.
Drilling CRS requires patience and the right technique. You generally need high-speed steel, HSS, bits, often ground to a sharper point, like 135 degrees. The critical things are slow speed, maybe under 750 RPM, and high constant pressure.
Why slow speed and high pressure?
You need to keep the bit cutting continuously, producing a chip. If you let up on the pressure or go too fast, the bit just rubs instead of cutting. Stainless steel work hardens incredibly quickly when rubbed. The surface becomes extremely hard, making it almost impossible to continue drilling.
Okay, slow and steady for CRES. Now the really hazardous one, magnesium. Very light, but that fire risk.
Magnesium requires extreme caution. It's used for things like gearbox housings where weight saving is critical, but magnesium chips, dust, filings, they are highly flammable.
So the main safety rule.
Keep all potential ignition sources, sparks, flames, extreme heat far away from any magnesium work area or debris. Even small particles can ignite easily and burn intensely.
And if a fire does start, what do you use to put it out?
Critically, never use water, foam, or CO2 extinguishers. Water on burning magnesium reacts violently, produces hydrogen gas, and can cause explosions.
Wow. Okay, so what do you use?
You need a Class D extinguishing agent specifically for combustible metals. Things like dry talc powder, dry sand, calcium carbonate, or powdered graphite work by smothering the fire, cutting off the oxygen supply. Apply it gently but thickly to cover the burning material completely.
Got it. Handle with extreme care and have the right extinguisher ready. What about forming magnesium? Is it easy to bend?
Not cold, no. Magnesium work hardens very quickly when bent cold, and it has significant springback, meaning it tends to return towards its original shape after bending. For accurate forming of structural parts, hot forming is the preferred method. The magnesium alloy is heated, usually somewhere around 450 degrees Fahrenheit, depending on the specific alloy.
Why hot forming?
Heating it makes it much more ductile, easier to form with less force, greatly reduces springback, and allows for better dimensional accuracy in the final part.
Makes sense. Okay, last special material. Titanium. The strong, lightweight champion used in high-temp areas like firewalls or for landing gear components.
Titanium is amazing stuff, about 30% stronger than steel, but only about half the weight. But it is notoriously difficult to machine, especially drilling.
What makes it so hard to drill?
It's very tough, and it generates a lot of heat very quickly when drilled.
Wow.
You absolutely need very sharp drill bits, usually made of carbide or high cobalt steel, like 8% cobalt. And similar to CRES, the technique is crucial. Very low speed and very high constant feed pressure. We're talking maybe 50 pounds of force pushing down just for a small 30 drill bit.
50 pounds. Why so much force?
Again, you have to keep it cutting. If you use too high a speed or not enough pressure, the friction creates intense heat. That heat causes the titanium chips to actually weld themselves to the cutting edges of the drill bit, instantly ruining the bit. Plus, the heat work hardens the titanium surface, making it even harder to drill. Low speed, high pressure, sharp bit, and often a good cutting fluid are essential.
Okay, challenging materials covered. Let's switch gears back to bending fundamentals. Flat pattern development. How do we figure out the size of the flat piece before we bend it? Starts with understanding the neutral axis, right?
Exactly. When you bend a piece of metal, the metal on the outside of the bend radius gets stretched, and the metal on the inside gets compressed. The neutral axis is an imaginary line somewhere within the thickness of the metal that doesn't stretch or compress. It stays its original length during the bend.
And where is it located? Right in the middle.
You'd think so, but not quite. Because the metal thins slightly on the outside of the bend, the neutral axis actually shifts a little bit inward, towards the inside radius of the bend. For calculation purposes in sheet metal layout, we generally approximate its position as being 0.445 times the material thickness, T, away from the inside surface of the bend.
0.445 times T from the inside.
Uh-huh.
Okay, how does that help us calculate the total flat length needed, total developed width, TDW?
The TDW is the total length of the flat pattern needed to produce the finished bent part. You calculate it by adding up the lengths of all the flat sections, legs and flanges, plus the length of the material used in the bends themselves, the bend allowance calculated using the neutral axis radius. The critical check is this. The calculated TDW must always be less than the sum of the outside dimensions of the finished part, measured to the sharp theoretical intersection points, the mold line dimensions, or MLDs.
Why less?
Because the metal bends around a radius, not a sharp 90-degree corner. It takes less material to go around the curve than it would to go all the way out to that theoretical sharp corner. If you calculated TDW equals or exceeds the sum of the MLDs, you've made a mistake in your bend allowance calculation.
Good check. Now, when you're actually at the break, ready to make the bend, what are the critical setup adjustments?
Two main things you have to get right before bending. First is the clamping pressure of the upper jaw or nose bar. You typically check it with a test strip of the same material. Clamp it, and the operating lever shouldn't feel spongy. It should clamp firmly, and you should be able to pull the lever fully over center to its stop without excessive force. Too loose, the metal slips during the bend. Too tight, you might damage the brake or the part.
Okay, clamping pressure, right. What's the second adjustment?
The nose gap. This is the clearance between the nose radius of the upper clamping bar and the bending leaf, the part that swings up to make the bend, when the leaf is brought up.
How do you set that?
You bring the bending leaf up, and using a scrap piece of the exact same material thickness as a feeler gauge, you adjust the gap so it's precisely one material thickness. Too small a gap, you risk pinching or shearing the metal. Too large, and the bend radius might be incorrect, or the bend might be distorted. Test strips are key for getting both pressure and gap right.
Okay, meticulous setup. Finally, let's talk inspection and compliance. When damage occurs, inspecting just the damage spot isn't enough, is it?
Absolutely not. Forces travel. You need to inspect the attaching structure well beyond the obvious damage. Look for signs that the impact or stress was transmitted further into the airframe.
What kind of signs are we looking for?
Things like wrinkled skin nearby, fastener holes that might be slightly elongated, popped rivets, or the telltale sign of movement in a riveted joint. Smoking rivets.
Smoking rivets. What does that mean?
It refers to a fine, dark, often greasy powder, which is aluminum oxide mixed with tiny metal particles that appears around the edge of a rivet head.
And what causes it?
It's evidence of fretting corrosion. It means the joint isn't tight anymore, and the rivet is moving slightly within the hole under load. That movement grinds the surfaces, creating the oxide powder. A smoking rivet is loose and must be replaced, usually with the next larger size.
Good visual cue to look for. Now, a critical point about materials. Substitution. If the exact alloy called for in the SRM isn't available, can we just use something stronger but maybe thinner?
That's a definite no and a common point of confusion. The rule is, replacement material must be structurally equivalent or better. If you have to substitute with a weaker alloy than the original, you must use a thicker gauge to maintain the same overall cross-sectional strength.
Okay, weaker means thicker.
But you generally cannot substitute with a thinner material, even if that thinner material has a higher tensile strength, like substituting thin 7075 T6 for thicker 2024 T3.
Why not? Isn't stronger better?
Because structural integrity isn't just about tensile strength, it's also about stiffness, buckling resistance, and torsional rigidity. These properties depend heavily on the material's thickness and shape, not just its ultimate strength. A thinner sheet, even if stronger, might buckle under compression loads long before the original thicker sheet would have, compromising the structure. Stick to the SRM or approved substitution data.
Very important distinction. And speaking of the SRM, what are the key documents governing these repairs?
The hierarchy is clear. The manufacturer's structural repair manual, SRM, for that specific aircraft model is the primary governing document. You must follow its instructions for any repair it covers.
What if the SRM doesn't cover a specific minor repair?
Then the FAA's Advisory Circular AC 43.13-1, Acceptable Methods, Techniques, and Practices Aircraft Inspection and Repair, can often be used as acceptable data, provided the repair method doesn't conflict with any manufacturer data.
And when does a repair become major and require more paperwork?
Certain repairs are automatically classified as major repairs. Things like splicing a wing spar, fabricating and installing a primary structural member like a longeron or frame, or repairing stressed skin damage that exceeds certain size limits, often cited as 6 inches in any direction, typically require the completion and filing of an FAA Form 337 major repair and alteration. This form documents exactly what was done and certifies its compliance.
Okay, SRM first, then AC 43.13 and Form 337 for major work. One last crucial safety check mention involves flight controls.
Yes, this is absolutely critical. Any repair or modification to a flight control surface, ailerons, elevators, rudders, trim tabs, that involves adding or changing weight, even slightly from paint or sealant, requires a mandatory rebalancing check before the aircraft is returned to service.
Why is balancing so critical?
Flight control surfaces are carefully balanced to prevent aerodynamic flutter. Flutter is a violent, uncontrolled oscillation that can occur at certain airspeeds if the control surface is out of balance or not stiff enough. It can destroy the control surface and lead to loss of control of the aircraft very quickly. Balancing ensures the center of gravity is correct relative to the hinge line. Don't skip it.
Wow. Okay, we've covered a huge amount of ground here, from understanding the forces like tension and shear, through the precision needed in layout with tools like combination squares and punches, to the specifics of cutting, grinding, forming with brakes and rollers, the critical rules for riveting alloy match, diameter, length, edge distance, pitch, avoiding elongated holes, deburring, dealing with tough materials like CRES, magnesium, titanium, and finally, the vital importance of inspection beyond the patch, proper material substitution, and following the regulatory requirements like the SRM and Form 337.
It really boils down to precision and adherence to established standards. A good repair isn't just strong, it accurately restores the original load path, the material properties, and the aerodynamic shape. It's those details, remembering the 1.5D for the shop head, getting the nose gap on the brake just right, checking for smoking rivets, using the next larger size for replacement that define airworthy work. When faced with damage, always think, what was this part designed to do? What forces act on it? That guides the repair strategy.
Which leads us to a final thought for you to consider. We've talked about meticulous manual layout, calculating bend allowance using formulas like the 0.445 xt for the neutral axis, maybe even using J-charts. But we also know that modern shops increasingly use sophisticated CAD software and CAM processes for incredible speed and accuracy. So here's the question. In an age of digital precision, why is it still fundamentally important for an expert technician to maintain deep proficiency in those manual layout and calculation methods? What's the real value of being able to determine a sightline by hand or calculate TDW from scratch when the computer can do it faster?
Think about it. That manual skill, that foundational understanding becomes your ultimate fallback, your insurance policy. It's what you rely on when the software glitches, the power goes out, or you encounter a unique repair situation the digital tools weren't programmed for. Being able to improvise accurately based on first principles, that is arguably the true hallmark of mastery in aircraft structural repair.